Hello and welcome to Conico Laboratory. Today I'll be giving a demonstration of a new Thermo-Differential Bypass Valve, which you see here, which is a completely new type of valve which acts as a one-way valve for heat flow, or a heat diode if you will. And we'll be demonstrating it by means of the setup behind me here. So I'll give you a quick introduction to the setup to start. Just move this monitor. So we have the same valve as here installed on this little storage tank here, and we're going to run a circuit through the valve and the storage tank, and the circuit consists of the heat exchanger here, which we can cool or heat using warm or cold taps, and from the heat exchanger we go through a circulation pump which directs the flow into the valve. Coming into the back of the valve, this is the inlet port here, and the flow can then either go straight back out, because this is essentially a T-section, in which case it goes up and through the tank, and then it comes back into this side of the valve. Or it can go straight into the valve, in which case it bypasses the tank completely. So in both cases the flows come together in the valve and come out through the outlet port coming up here. After that it passes through this flow gauge here and back through the heat exchanger. To actually monitor what is going on, we've installed temperature sensors, 3 temperature sensors, one in the inlet flow and also one of the tank at the exact position where the valve is installed, and one of the outlet flow. And based on these temperatures we can see in which position the valve is, which we can also see because the valve is transparent of course, but more importantly we can see how well the valve closes off each inlet, which we'll be showing now. So now we're looking at the setup a bit more close up, so that we can actually see all the measurements and all the data on the screen. So what we're looking at on the screen are the temperature measurements of the 3 sensors, where the red line is the tank temperature, and the blue line is the inlet temperature, and the green line is the outlet temperature. So at the moment the red line is higher than the green and the blue line, because the tank temperature is higher than the inlet temperature, which means that the valve is completely bypassing the flow, which means so the inlet and the outlet temperature at the moment are the same. That's why the blue line and the green line are completely overlapping. And above the graph you can see the actual temperatures of the different sensors. So on top is the inlet temperature, which is 33.02 at the moment, the tank temperature, which is 35.31 at the moment, and the outlet temperature, which is 33.03 at the moment, 3.02. So as you see, the temperatures of the inlet and the outlet are exactly the same at the moment. So the valve is 100% bypassing the flow. No flow is going through the tank at all. So to give you a quick demonstration, at the moment there is no hot or cold taps running through the heat exchanger, so it's just running in a closed circuit, no heat being added or withdrawn, and you can see it's completely stable. What I'll start doing now is start adding some hot water, hot tap water or cold tap water to the heat exchanger to heat or cool the circuit, and then you will see the temperatures changing and the valve changing position. So to start, I will start heating the circuit now, so you can see the valve switching and how the temperatures change. So I've turned on the hot tap, and it may take a while for the hot water to come through. Now you see the temperature increasing, the inlet, the blue line now overtaking the red line, which means that the valve should now start to switch. So you look at the valve now, it has fully switched. So in a few seconds of switching time, the valve is now completely moved to the open position. So now the flow is directed via the tank, which you can see because the outlet temperature, the green line, is now starting to follow the red line, whereas the inlet temperature is much higher. And just to show you the reverse switching, I will now switch on the cold tap. And as cold water will start coming through the heat exchanger, and you will see the temperature dropping. There it comes. As soon as it crosses the red line again, the valve in a matter just around a second immediately switches, because it's such a quick temperature change, to now bypass the tank again, which makes sure that no heat is being withdrawn by the cold flow from the tank. So as you see now from this graph, heat initially was bypassed, then it was opened because heat could be delivered to the tank, but as soon as the inflow cooled down again, the tank was bypassed again to avoid heat being withdrawn from the tank. So now to explain how exactly the valve works, here is the valve again. I'll just first go through how it is installed again. So here is the inlet flow into the valve, which is at the back of the installation here. And from that inlet flow, the flow can either go straight back out of the valve, in which case first passes through the heat exchanger or the buffer tank, and then comes back into the other end of the valve. Or it can go straight into the valve, and in that case the buffer tank or the heat exchanger is bypassed, as you see here as well. So how does the switching actually work? Well, we're going to look inside the valve now. So here you see the actuator sitting in one half of the valve, and you can see that the actuator can tilt, and it can tilt to close off the inlet. So at the moment it is tilting and pushing against the bypass port, in which case the liquid coming in will be directed through the heat exchanger. But it can also tilt the other direction and close off the port coming from the heat exchanger, in which case it will bypass. And the way that the actuator pivots is that, first explain this actuator. So it consists of a float in the middle, which has a little dividing wall in the middle of the float inside, and the dividing wall has a hole in the bottom. So basically this actuator is filled with working liquid, and the working liquid will always want to move towards the colder side of the actuator, driven by the vapor pressure, which is always higher on the warmer side of the actuator. So at the moment all the liquid is on this side of the actuator, which is why it's tilting that way. But if I then heat up this side of the actuator with my hand, because my hand should be warmer than the ambient temperature, then all the liquid will start transferring to the other side of the actuator, and the actuator will start tilting in the other direction. As you see here, now it's tilting to the other direction. And if I again heat up this side with my hand, the liquid will now start transferring back to the other side, back to the original side, because now this side of the actuator is warmer. So you see now all the liquid has transferred back to this side again. So this movement of the liquid inside the actuator is what makes the actuator tilt and directs the flow into the appropriate direction. So now we're looking at the setup a bit more close-up to get an even better look at what's going on, and we'll do the experiment a bit slower, heating up slower and cooling slower, so we can see very well how accurate the valve is when in its switching position. So we're starting again with the valve being in the bypass position, because the inlet temperature is lower than the tank temperature, and you will see because then the blue and the green line are below the red line and they are fully overlapping. So the valves both are at 33.64, so it's 100% closure, even though the temperature is only just over a degree below the tank temperature. So now I'm going to very slowly open up the warm tap to add some heat to the heat exchanger to increase the inlet temperature. So the inlet temperature is now slowly starting to increase. And the temperature inlet is now 34.31, while the tank temperature is 34.84. So we're now at half a degree lower than the tank temperature, and the closure is still complete. And we're now, you can also see from the valve it's still in the bypass position, and right about now the temperature of the inlet and the tank are the same. It's just, so from this point on the valve can start moving to the open position, but this particular valve actually has a slight bias towards closing off the tank to make sure that there is never any heat withdrawn from the system, and so a small offset of a couple of tenths of degrees, up to a degree, is required for the valve to actually move to the open position. So now the inlet temperature is at 36.2, where the tank temperature is 35, and now you can see the valve is really switching, and now it is switched completely through. So it is used this offset of around 1 degree to make sure that no heat can be withdrawn, because we need this offset when we start cooling to make sure that the valve is switched back to the bypass position when we are cooling before it drops below the red line. So now we'll close the hot tap and slightly open the cold tap. And still some hot water in the lines. So as you can see, the temperature of the inlet is still increasing a bit, but it will soon start decreasing. And there you see that the valve is now switched position before the inlet temperature actually reaches the tank temperature. So this gives you the 100% guarantee that heat is never drawn from the tank, and heat can only be added to the tank when using the thermo-differential bypass valve. So now that we have seen how the valve works and how well it works in acting as a one-way valve for heat flow, or heat diode, I want to tell you a bit more about an example of an application for this valve, which is an application which is very similar to the way it is set up here. And that application is to create a solar system where you no longer need any differential controller or any controller at all. And in such a solar system, well, this heat exchanger would represent the solar panel, and this pump here would be a circulation pump that is driven by, for example, by a PV panel, a small PV panel, which would then drive a DC pump whenever the sun is shining. So the pump will run whenever the sun shines. And so the valve will then take care of the differential control element of the system, because it will make sure that the circulation through the solar panel will only pass through your solar tank when it can actually deliver heat. But at times when there is very low irradiation and your tank might be very hot, your solar panel will not be able to deliver heat, and in that case the valve will bypass your solar storage tank to make sure that no heat is withdrawn from the system. And as you have seen, the valve is very accurate in switching and will thereby also increase the efficiency compared to when using a system with a differential controller, because the system will be able to operate at a lower temperature because it requires only less than 1 degree temperature difference before it can collect heat, instead of the typical 6 degrees that a differential controller takes before it switches on. And more importantly, any cold water that is in the pipes at the startup of a solar system will not go into the tank as with a conventional system, but will be bypassed, so that you avoid a lot of heat losses in the piping by using this valve as well. So all in all, you will have a much simpler system without any electronics, without even the need for a general electricity connection, a completely autonomous system with only mechanical components apart from a DC pump powered by a PV panel. Thank you.